Канадського королівського наукового товариства, так само і члена Лондонського ліннеївського товариства. Доповідь Perfect Storm, Climate Change, Disease і ми буде представлена англійською мовою, але я просив, щоб це було дещо адаптовано для нашого. Якщо у когось потім після доповіді будуть питання, то ви можете їх задавати, навіть якщо ці питання будуть українською. Якщо можна, то англійською, але ми що-небудь придумаємо. Дякую за увагу. Будь ласка.
First of all, I would like to thank you very much for the invitation. Even before 1989, there were a few things about this part of the world that North Americans knew, and one of them was this research institute and the history of the researchers in it. But when I was a student growing up in Washington, D.C., back in the Pleistocene, I never had any hope that I would ever see this place. And so it's a wonderful honor to be here on many levels. The problem is that today my job is to ruin your day and change your life, especially for the students. The good news is I will not be speaking in Hungarian. The bad news is I will not be speaking in Ukrainian. So you'll have to put up with something in the middle, which is American English, or what Americans call English. Now, the problem, okay? The problem is that there are a lot of diseases on this planet. And there are new diseases and outbreaks of old diseases in new places and in new hosts every day. There are websites like Outbreak.com that are just, if you want to feel like the world is coming to an end, just read Outbreak.com every morning. This is a long list. Today, the newest news today is that there's probably going to be a major dengue fever outbreak in the Caribbean this year. Oh, wonderful. But even worse than that is that now, when we hear news like that, we go, oh, yeah, it's another disease outbreak. And this is an indication of how great the problem is. We have diseases that are emerging on this planet every day. They are not just affecting human beings, they're also affecting the plants and animals that we depend on for food and for commerce. And these outbreaks are happening much more rapidly than our theories about the evolution of pathogen host systems would predict. So this is not just a problem for the world at large, for the practical world. This is also a challenge for evolutionary biology, because clearly we have been missing something. We failed to anticipate the emerging disease crisis. If you just read the newspaper reports, the news accounts, the online news accounts, you might have the impression that the emerging disease problem is just a problem that's associated with a few really nasty viruses in the tropics, things like Zika and Ebola and dengue. But the reality is that viral infections actually are the least expensive kind of pathogens on the planet. Bacterial infections cost the world much more than viruses every year. Helminths and protists cost the world more than bacteria every year. And we are now seeing old diseases returning. So malaria has now returned to southern Europe. Schistosomiasis has been reestablished on Corsica. And after 5 years, the public health people have decided that perhaps there's a non-human reservoir on Corsica that explains this. So we're very, very slow to react. We're very slow to understand what's happening. We're not anticipating. 3 years before the malaria outbreaks in Tuscany, southern France, and southern Switzerland last August, 3 years before that, a research group in Spain had published an article saying Anopheles mosquitoes are now capable of surviving the winters in southern Europe because the winter temperatures are mild enough. Nobody paid any attention. And in fact, when a 6-year-old Italian girl died in a hospital in Tuscany, the hospital spokesman said, "We don't understand this. This little girl never traveled outside of Italy, and we know there's no malaria in Italy. So we don't understand how this happened." This is the state of the world. This is the state of our preparedness now. They are everywhere. They're transmitted in everything we do. Everything we do as human beings can bring us into contact in one way or another, potentially with a pathogen. The same thing is true for our crops and our livestock. They're found in rural areas, they're found in urban areas, they're found in the wildlands, basically everywhere. They're in developing countries, they're in developed countries, they're in the tropics, and they're outside of the tropics now. And they're moving out of the tropics even faster than the tropics is expanding north and south. They are a national security problem for every country on this planet. They're a problem for water security, food security, public health security, sociocultural security, and this includes things like coping with migrants, and economic security, because every country in the world has budget problems right now. And any increased expense on the public health system or the agricultural health system means less money someplace else. And it's costly. It's much more costly than anybody associated with organizations like the World Health Organization or the Centers for Disease Control will admit in public. It took Eric Hoberg and Walter Wieger and me 6 months to dig out even a conservative estimate of how much emerging infectious diseases are costing the planet every year now. And a conservative estimate is larger than the GDP, the gross domestic product, of all but 15 countries. If Hungary wanted to pay the bill for the world's emerging disease costs for 1 year, it would cost them their GDP for 4 years. And the countries, of course, that are most heavily hit by emerging diseases are the ones that cannot afford it the most. They're the ones that have the least money. So there's a really, really big problem. If we are not already at a point where healthcare costs are unsustainable, we will be there very shortly, globally. There is no country on the planet that is not falling behind with respect to the amount of money they have to pay for healthcare, for diseases, for emerging diseases, and how little return they're getting for their money. So the question for evolutionary biologists, because one of the things we say in our book that's coming out next year is that it's nobody's fault but everybody's to blame. And the scientific community has a lot of blame. Evolutionary biologists in particular, as I said, we failed to anticipate the emerging disease crisis. And we failed to anticipate it because during the 1950s and 1960s and on, we created models of coevolution that kept us from recognizing what was happening when it was happening. So we not only don't understand why there's this emerging disease crisis, we don't understand why we're losing the battle. So what's wrong with us, the evolutionary biologists in the audience, people like me? The problem is that our scientific beliefs about the nature of pathogen host systems and the evolution and ecology of pathogen host systems does not correspond with what we're actually seeing today. So we have a very drastic mismatch between theory and observation. Now, in the 20th century, there were two major models of coevolution. There was a lot of activity. There was a lot of thought for 100 years about what we now call evolution. But by the end of the 20th century, those thoughts had coalesced into two major categories, or two major classes of coevolutionary models. One is called the coevolutionary arms race model, which developed in the United States, not surprisingly, in the middle of the Cold War, and so that's why it ended up being called the coevolutionary arms race model. And then more recently, there is John Thompson's geographic mosaic theory of coevolution. Now, the coevolutionary arms race model, which is usually associated with a paper in 1964 by Ehrlich and Raven in the journal Evolution, but which was actually described mathematically in a paper also in Evolution 6 years before Ehrlich and Raven published their paper, and they never cited it, by a mathematician named Mode. And the reason Ehrlich and Raven didn't cite Mode's paper was because Mode was working with agricultural diseases, and Ehrlich and Raven were working with butterflies and plants. Obviously, these things must not have anything to do with each other, and yet they both described exactly the same phenomenon. And that's one in which you have a theory of progressive specialization, ecological specialization, in the association between particular pathogens and their hosts, with the pathogens evolving traits to attack the hosts and the hosts counter-evolving traits to defend themselves from the pathogens. The geographic mosaic theory of coevolution allows the possibility of coevolutionary arms race interactions but doesn't require it. Okay, coevolution, in some ways it's a more general model. Coevolution, according to Thompson's theory, occurs when generalist parasites are distributed among multiple hosts in different places. Each of the hosts is assumed to represent a slightly different resource, slightly different selection regime, and when these different host pathogen populations are isolated geographically, you have the emergence of multiple new specialist pathogen host situations. Now, the interesting thing about this is that both of these categories of models agree on one thing: that pathogens are highly specialized on their hosts, and once a strong coevolutionary dynamic has been established, the longer the host and pathogen are associated with each other, the less the chances that that pathogen is going to be capable of moving into a new host. In other words, coevolutionary thought, as of the end of the 20th century, led us to believe that evolution was the best firewall we had against emerging diseases. Coevolution was going to keep emerging diseases at a minimum, because emerging disease requires that pathogens get into new hosts. And this led to, in the early 20th century, to what the insect plant people like Sal Augusta, called the parasite paradox, or the pathogen paradox. There are not an equal number of generalist and specialist pathogens on this planet. There are not an equal number of generalist and specialist herbivorous insects on this planet. The vast majority of them are highly specialized, especially with respect to host range, that is, the number of hosts utilized. But it also turns out that host range within groups of pathogens, including within groups of phytophagous insects, host range changes over time. And we have all of these emerging diseases occurring in real time. So something is going on much more rapidly and in a much more complicated way than our coevolutionary models of the 20th century suggested. Phylogenetic comparisons, which were not possible until the last 25 years of the 20th century, essentially, all of them have shown that pathogens moving around among hosts and changing their host range through time is actually the evolutionary pattern. This has always been the case. So we need a new paradigm of something. We don't even know what to call it. Well, we do. I called it the Stockholm paradigm because most of the insights that I've gained about it were done in conjunction with collaborations with the insect plant people at Stockholm University. So how do we resolve this paradox that pathogens are in fact highly specialized ecologically? Most of them at any one point in time in any one place have very restricted host ranges, but they're capable of moving among hosts really readily. Well, it turns out that one of the things we have to explain is this whole business about host range evolution. Okay, I'm not going to use the term host specificity because we don't believe that there is any such thing as host specificity. Just as I'm not going to use terms specialist and generalist because those are non-evolutionary terms. Organisms can specialize or generalize, but specialists and generalists can't. They are either one thing or another. And so they either exist or they go extinct. They don't diversify. And part of the problem we've had is the language that we've used. And the history of some of that language is quite interesting, and it was quite rational at one point in time, but it's not working. Okay? So here's what we find when we look at host range, that is, the number of host species and the phylogenetic breadth, the phylogenetic distribution of host species utilized by particular groups of pathogens or phytophagous insects. What we find is that over time, the host range expands and contracts and expands and contracts and expands and contracts. Now, we have a really good theory to explain how things that are generalized can become specialized. I mean, we know that really well. In fact, Darwin's entire theory was based on the assumption that everything is specialized in some way. Those were the adaptations. But what we've never had is an explanation for how something that was highly specialized could be generalized. So if evolution or coevolution is some sort of process of continually producing new specialists, where did the generalists come from? You might be interested to know that the concept of ecological generalists is only about 50 years old. Until about 50 years ago, it never even occurred to anybody that there could even be any such thing. It was an idea that was thought up to try to explain this problem of how do we get new specialists all the time. So what this oscillation is what the Swedes call the oscillation hypothesis. This phylogenetic pattern of host range is doing this in evolutionary time. What that implies is not only that generalized species can become highly specialized, but also that highly specialized species can become generalized. So that there's one general mechanism that explains both the host range expansion and the host range contraction, or the generalization and specialization, generalization and specialization. And it turns out that the key element to this is understanding a concept that Dan Jansen proposed in 1985 called ecological fitting. Basically what ecological fitting says is this: every species lives in a place doing something that works really well for where they live and what's available to them. But every one of those species could live someplace else as well. Now, in terms of pathogen-host associations, what that means is that even if a pathogen occurs in only one place and infects only one host in that one place, that pathogen will still be capable, without any new genetic mutations at all, is capable of infecting other hosts in other places. So that means that the capacity to live in multiple hosts is always present in pathogens that are highly specialized. Everything we measure about them in terms of their transmission dynamics, their microhabitat preferences are highly specialized, but their host range restriction, the number of hosts that they infect, is highly contextual. It's not a built-in genetic deficit. It's contextual. It's part of their ecology. It's part of their ecological context. And we can always assume that there are other species in other places that are susceptible to any pathogen, any particular pathogen, but are not infecting, the pathogen's not infecting those other hosts simply because they have never come into contact with each other. And one of the side products of that is that if you've never come into contact with a pathogen before, even though you're susceptible, there's been no possibility of selection for resistance in your population. So that means two things. If you ever come into contact with that pathogen will recognize you as just more of the same real estate and will immediately add you to its list of hosts. And you will have no resistance to it. And this is because, and as I said, we don't use the term host specificity anymore because pathogens are not specialized on hosts. They're specialized on traits that hosts have. So there's no conflict between saying that pathogens are extremely ecologically specialized and saying there's no such thing as host specificity. And the reason for that is because the traits that pathogens are specialized on are found in hosts. So of course there's some correlation between hosts and pathogens. But this is one of the things that the phylogenetics revolution showed us, was that there are a whole lot of ways that this can be true. For example, here's sort of the old-fashioned model of host pathogen associations. So here's host G, and up here this I, that one, that's the pathogen. And this is, the pathogen is restricted to the host. This is what we would call extreme host specificity. They are a very specialized pathogen. And what I've done here on the phylogeny of the host is I've made this line very thick. And that represents the phylogenetic distribution of the resource or resource base that the pathogens are specialized on. And in this particular case, because the pathogen is specialized on a resource that is only found in one host, that pathogen can only survive in one host. That pathogen still has the ability to move around if the host moves around geographically.